And what if a robot could lift 100 times its own weight? Silent, flexible, and without a single motor. That sounds like science fiction, but it is becoming reality. Researchers from one of the largest universities in the United States have just published in the country's most respected scientific journal a discovery that could change forever the way robots work. They created artificial muscles powered by air, inspired directly by human muscles, capable of operating in boiling water, traversing the rubble of a collapsed building, and lifting loads that no conventional system can handle. What comes next will surprise even those who have been following robotics for years. Want to understand everything? Then watch the video all the way to the end and I'll explain it all to you. But first, leave your like and subscribe to the channel. That way, you'll stay informed about the latest news in robotics. Think of a robot that seems to have real muscles, that bends, contracts, stretches, and still carries 100 times its own weight. No motor, no noise, no cables plugged into a wall outlet. This is not a laboratory promise for 30 years from now. This was published last week in one of the most prestigious scientific journals in the world. Scientists from the United States developed a new type of air-powered artificial muscle that allows robots to lift up to 100 times their own weight without relying on heavy motors and external energy systems. The work was conducted at Arizona State University, and the results were published in the Proceedings of the National Academy of Sciences, a global reference journal in science and technology. The technical name for what they created is HARP, an acronym for Helical Anisotropically Reinforced Polymer Actuator, that is, a polymeric actuator with helical anisotropic reinforcement. For those who are not engineers, these are small polymer tubes, a type of high-performance plastic, arranged in a spiral shape, which contract and expand when they receive a small amount of air, exactly like a real muscle does when the brain sends a signal. What makes this discovery different from everything that came before? The answer lies in a limitation that anyone who has ever tried to carry a robot in their arms has already noticed. Ordinary robots are absurdly heavy. Today's quadruped robots, those with 4 legs, like robotic dogs, are significantly limited in mobility because they are generally motor-driven and tend to be very heavy and less flexible. HARP actuators solve this problem in a simple, biologically inspired way. They swap the electric motor for air. The work was so well received by the scientific community and the private sector that the university team has already filed a provisional patent. More than that, the team received an academic grant from Nvidia to continue developing the research. Nvidia, the company that manufactures the most widely used artificial intelligence chips in the world, does not usually distribute resources to just any project. The fact that it supported this one is a clear signal that the market already sees a real application here. The research is not limited to creating artificial muscles for specific tasks. Instead, the scientists developed a versatile system that allows the technology to be adapted for various applications in a more affordable and practical way. But what does this mean in real life? What applications can this technology have when it leaves the laboratory? How can it impact your life, work in factories, care for the elderly, or even survival in emergency situations such as an earthquake? To understand why this artificial muscle is so important, it is first necessary to understand why today's robots have so many problems with their own weight. A traditional robot runs on electric motors. Motors weigh. They need gearboxes to transmit force. They need large batteries to run long enough. And the heavier the robot, the more energy it consumes, which requires even larger batteries, which weigh even more. It is a vicious cycle that limits what a robot can do, where it can go, and for how long. HARP actuators break this cycle in a surprisingly simple way. These muscles look like small tubes coiled like cavatappi, which is a hollow, ridged, corkscrew-shaped pasta. When we inflate them by applying a little air, they expand and contract. Cavatappi is a type of Italian pasta, and that is exactly the shape researchers used to describe their creation. Small, light, spiraled, and when air enters, incredibly powerful. The key word here is anisotropic. Without getting into advanced physics, anisotropic materials behave differently depending on the direction in which force is applied. In the case of HARP, this means that researchers managed to program, through the structure of the material, so that when inflated, the tube contracts in a specific direction with great precision. Like a bicep, when air enters, the muscle shortens and lifts. When air exits, it relaxes. Because of its versatility and adaptability, we were able to significantly reduce the pressure requirement, which allowed us to build a robot that could walk independently without any external power source, carrying everything it needs with itself, explained one of the researchers. This is revolutionary. The quadruped robot built by the university laboratory using these artificial muscles walks without being connected to anything. No wires, no air hoses connected to an external compressor. It carries its own energy source. This completely changes what is possible to do with a robot outside of a controlled environment. But the performance goes beyond energy autonomy. HARP actuators can withstand extreme heat, which is why, according to the team, they can be used in industrial rinsing, marine exploration, and sample collection near thermal vents. Think of robots working near underwater volcanoes, or inside foundries, or in industrial processes where temperature destroys any conventional electronics. HARP survives all of that. Their flexibility, rotational capability, and gripping ability also make them suitable for agricultural and industrial applications. And the laboratory did not stop at the muscles of the quadruped robot. Another project in the laboratory is the Bionic elephant arm, a soft, robotic arm inspired by the flexibility and dexterity of an elephant's trunk. This bio-inspired device allows the arm to reach over, under, and around obstacles with ease, making it particularly suitable for inspection and manipulation tasks in industrial environments. There is also a third device coming out of the same laboratory, a lumbar support device, a vest that combines soft materials with adjustable assistance to reduce overload during heavy lifting while remaining light and comfortable. 3 different devices, all using the same philosophy. Replace rigidity with flexibility, weight with lightness, motor with air, and all published in a single research paper, which is unusual and reveals the breadth of what the Arizona State University team built. What no one expected was exactly the level of autonomy achieved. A robot with air muscles, carrying its own energy source, functioning in environments where normal robots simply cannot enter. That was not in the plans of most robotics teams in the world, and it is happening now. The most immediate impact of this technology is in the field of disaster response. In disaster response, soft robots will move through rubble or collapsed buildings to search for survivors. Their flexible bodies allow them to fit into tight spaces without causing further damage. At home, they could safely help older adults with daily activities, such as reaching items on shelves and assisting with simple tasks. For sectors such as construction, mining, healthcare, and elderly care, this is not just an opportunity. It is a solution to a problem that has been worsening as the population ages and certain professions become increasingly difficult to fill with human labor. The muscles can be used in agriculture, industry, healthcare, household tasks, and even in future space missions. For companies operating in these sectors, from exoskeleton manufacturers to aerospace companies, the window to position themselves in this market is opening now, and those who delay may fall behind. Publication in the PNAS, one of the most demanding scientific journals in the world, where fewer than 15% of submitted articles ever get published, is itself already a signal of the quality of the research. But what are experts outside of Arizona State University saying? A comprehensive review published in December 2025 in the journal MD-PY Actuators highlights that pneumatic artificial muscles have evolved from braided designs of the 1950s to a diverse class of actuators with high power-to-weight ratios, compliance, and safe interaction with humans, with applications spanning rehabilitation, assistive robotics, aerospace, and adaptive structures. The work of Arizona State University fits perfectly into this trajectory, but goes further by offering a general framework rather than just a specific solution. Challenges in soft robotics, such as achieving complex motion control, incorporating feedback systems, modeling the dynamics of soft materials, and replicating biological muscle efficiency with artificial muscles, are still widely discussed in the scientific literature. What the Arizona State University team presents is a concrete response to at least 2 of those challenges. They created a muscle that operates autonomously, without external energy sources, and that functions under extreme conditions that conventional elastic materials cannot withstand. From an ethical and regulatory standpoint, the central question that emerges is that of safety in environments shared with humans. Soft robots, by definition, cause less damage in accidental collisions than rigid robots, and that is a strong argument for their adoption in domestic and hospital contexts. In the end, these artificial muscles are softer, more flexible, and safer. Being smaller and lighter, they can be used in many different types of robots without the risk of pinching or hurting people, as happens with today's rigid robots. This is relevant for regulators who need to define safety standards for robots that physically interact with people, something that does not yet exist in most countries. But how do HARP actuators compare to what already exists on the market? That is the question robotics engineers are asking now. The Atlas, from Boston Dynamics, is the most advanced humanoid robot in commercial production in the world in 2026. The Atlas has 56 degrees of freedom, fully rotational joints, a reach of 2.3 meters, and the strength to lift up to 50 kilograms. It runs on electricity and is an extraordinary machine, but it weighs around 89 kilograms and operates in controlled industrial environments, factory floors, logistics, assembly. All Atlas robots planned for 2026 are already reserved. The first fleets will be sent to Hyundai and Google DeepMind in the coming months. That is to say, the Atlas will not enter collapsed buildings to rescue survivors, will not pass through 15-centimeter gaps, and will not work inside boiling water. That is exactly where robots with HARP muscles stand out. They are not competing with the Atlas. While the Atlas is a strong worker for factories, HARP robots will function like paramedics. They will be light, silent, flexible, and able to enter places where the Atlas simply cannot fit. The great differentiating factor of the Arizona State University researchers is not just the strength of the muscle. It is managing to bring together in the same system 4 important things: strength, lightness, autonomy, and resistance to extreme conditions. Research published in the journal NPJ Robotics from Nature explores fiber-type artificial muscles for robotic actuation, pointing out that soft and wearable robotics is one of the most promising areas for these devices. The scientific consensus is converging. The future of robots is not necessarily more metallic and heavier. It is softer, lighter, and closer to biology. What makes the work of Arizona State University especially relevant in this context is that it is not limited to a specific device. The team created a platform, a set of design principles that can be adapted to different sizes, applications, and uses. That is far more difficult and far more valuable than creating a single device that does only one thing. It is the kind of research that can give rise to an entire industry. What the Arizona State University team published in the PNAS is not just a technical novelty. It is a paradigm shift in the way we think about and build robots. For decades, robotics was dominated by a logic of rigidity. The more precise and stronger, the better. The researchers at Arizona State University proved that there is another path, a lighter, quieter path, more similar to what nature already invented millions of years ago. When a robot with air muscles can lift 100 times its own weight, operate in boiling water, and still walk without any wire connected, the boundary between machine and biological organism begins to fade in a concrete way, not a metaphorical one. The question that remains is this: if a soft, light robot powered only by air can already do all of this today, what will happen to the professions that depend on brute physical strength, such as firefighters, rescue workers, and miners, when these robots reach the market at real scale? Leave your opinion in the comments. If you enjoyed the video, leave your like and subscribe to the channel. That way, you will always receive notifications of new videos. Until next time.